Hey guys, welcome to lesson 3.8, solving trigonomic equations in degrees. So before we do anything, make sure that your calculator is set on degrees, and we'll continue on. Basically, a couple of things I want you to be aware of is the sine ratio is y over r, cos is x over r, and tan is y over x. Keep in mind the cast rule, and again, because we're working in degrees today, the special triangles we're going to work with are with degrees and not radians in the inside for the angles. So for our first question, what I want you to do is I want you to kind of treat it as if it was some linear equation. So basically when you're trying to solve for, let's say, x minus 1 equals 0, well, what you would do is take the 1 and move it to the other side. So kind of the same idea here. So the first thing that we're going to do is take that 1 and move it to the other side. So cos x equals 1. So one thing to note is that this equation has an infinite number of solutions if I don't set a specific interval. So, and that's because cos goes on and on forever. Its domain is the set of any real numbers. So what we're going to do, and there's a little typo here, so make sure you fix it. We're going to solve this equation for x as if it were in between 0 degrees and 360 degrees. Now, when we are solving for cos ratios or sine ratios that are equal to 1, 0, or negative 1, I personally find it's always best to go to the graph, because the graph is it tells you really easily where 1, 0, and negative 1 is. So in this case, where does cos x equal 1? Well, here's our cos graph. If you take a look at 0 degrees, we get a maximum of 1. And actually, this scale should be in degrees. And also, again, at 360 degrees, we also get a maximum of 1. Okay, so one way to find your answers is just to clearly take a look at the graph and see where cos equals 1. A second way to do it is just to say, set up your equation, so cos x equals 1. Now, again, we're trying to find the angle x here that will give us a ratio of 1. So one thing we can do is take the inverse of 1. Again, make sure your calculator is set in degrees, and you should get 0, which corresponds to what we have on our graph. To get any subsequent angles that will also give you 1, we could take our original answer and add 360 degrees. So kind of like finding coterminal angles. Add 360 degrees. So the next time that the cos graph will equal 1 is when x equals 360 degrees. Okay, so for example 2, again, you want to isolate tan x. So the first thing we're going to do is move this positive 1 over to the other side. So root 3 tan x equals negative 1. And then to isolate tan x, we divide both sides by root 3. So we're left with tan x equals negative 1 over root 3. Now, this has just turned into a question that we did at the very beginning of the unit. Basically, we want to first find out where is tan negative. So we take a look at our quadrants here. Well, tan is negative in the second quadrant, so in the sine quadrant, and in the cos quadrant, or in the fourth quadrant. And now I need to find out those related acute angles. But taking a look at this ratio, I see 1 and root 3. That tells me that I should probably be thinking about special triangles. Remember that tan is really y over x. So in this case, along my y values, I'm going to put a 1, and my x value is going to be root 3. So again, root 3 and 1. Now in this triangle here in the second quadrant, the 1 will be positive because it's up on the y-axis, but the x will be negative, which will give us a negative 1 over root 3. In the fourth quadrant, this time the x is positive, but the y coordinate should be negative because we're going down on the y-axis. So now that we've perfectly labeled our side lengths, the next thing we should do is come up with the related acute angles. Because this is a special triangle, the opposite angle from side 1 would be 30 degrees. And again, this related angle here would be 30 degrees. So to solve for x, you're going to find two values. As always, you start at the standard position and you rotate counterclockwise until you hit the first terminal arm. So the x, or the angle that we're trying to find, is this green angle here. So to find the first possible value, this green angle could have went all the way to the other side, so all the way to 180 degrees, but we stopped 30 degrees before that. So 180 minus 30 gives us 150 degrees. Now our second possible answer, again, start at the terminal arm and rotate counterclockwise. So for x2, we could have gone full circle, which is 360 degrees, but we, again, stopped 30 degrees before that, so 330 is another possible answer. Now you can double check this on your calculator. Take 150 degrees, again, make sure your calculator is set on degrees, and sub it in for x. Do root 3 times the tan of 150, and then add 1. And see what you get. Hopefully it's 0. Same thing with 330. So these questions you can always double check and make sure that you're on the right track during a test. Okay, next example. In these examples here, a little bit different than the previous examples because we have sine squared. So these end up looking like quadratic functions. So in the first couple of examples, we tried to isolate the sine or the cos or whatever the trig function was. In this case, we're going to treat it like a quadratic. And whenever we work with quadratics, you want to move everything to one side so that one side equals 0. So we're going to go ahead and do that. So 2 sine squared x. I'm going to move this 5 sine x to the other side. Minus 3 equals 0. So it's very similar to a trinomial. Let's pretend it was 2x squared minus 5x minus 3. So if you were working with that type of question, in fact, if you really wanted to, you can go ahead and make that substitution if it's more helpful to see. So I can change this question to look like 2a squared minus 5a minus 3. And then this is just this, a complex trinomial, and we can factor it out. If factoring doesn't work, you can always rely on quadratic formula. In this case, we are looking for two numbers that multiply to -6 and add to -5. Okay, because it is a complex trinomial, and those two numbers end up being -6 and 1. And again, because it's a complex trinomial, I can't just put these two numbers in brackets. I need to decompose. So we'll rewrite this equation as 2a squared minus 6a plus 1a minus 3. So we decomposed this -5a. And now we can do some factor by grouping. So in this first group, I can common factor a 2a, and I'm left with a minus 3. And in the second group, nothing to common factor out, but we know we are on the right track because if we kept it as its own group, it's still a minus 3, and now I can see that we have two brackets, well, two terms, each with a bracket a minus 3. So we can common factor that a minus 3 out, and we're left with 2a plus 1. Okay, now if we were to continue to solve, because we need to know what a is here, in this case, I would say a equals 3, and in the second bracket, we know that a is equal to -1/2. Okay, because you set the bracket equal to 0, move the 1 over, and divide it by 2. Now remember, A was never part of the question. So what we need to do now is go back and replace the A with the sine x. Okay, so really what we have here is sine x is equal to 3 and sine x equal to negative 1/2. Now we need to solve for the angle x. Kind of recall the sine graph. Looks like this. Its maximum is 1 and its minimum is negative 1. There is no value for the angle x here that would ever make this positive 3. So in this case here, there would be no solution. So we can focus on just this case. Now in this case I see 1/2. This kind of leads me to believe that we can work with some special triangles. So what I'm going to do, again as we did in the last example, I'm going to indicate where sine is negative. So sine is negative in the 3rd quadrant and also in the 4th quadrant. And again, recall that sine is really y over r. So if I labeled my diagram, my y value and my r values. Okay, so this does look like the makings of a special triangle. Again, opposite of the 1 would be 30 degrees. So now that I know the related acute angle, I can start listing the values or the possible values for our angle x. So the first one, as always, we start in standard position and we rotate counterclockwise until we hit the first terminal arm. So x1 is really 180 degrees plus 30 more. Which would give us 210 degrees. And then angle 2 or x2, start at standard position, rotate counterclockwise. So this blue circle almost went all the way around, but we stopped 30 degrees before that. So 330 is another possible answer. Okay, so then that's it. Again, you can take a look at your answers and sub it back into the original equation and make sure that you're doing a left side, right side check. Okay, last example for today. A little bit different than the last one we did because, yes, it's quadratic because we have a cos squared, but now we have a cos squared and a sine. So having two different types of trig ratios in a question would be a little bit difficult to work with. So what we're going to do is use the Pythagorean identity so that way we can replace one of these things so that we're always working with just or one type of trig ratio. So the one you want to replace is the one with the squared. Let's replace the cos squared. Now taking a look at the Pythagorean identity, I can rewrite it as cos squared is equal to 1 minus the sine squared. So we'll rewrite our question here as 4 times 1 minus sine squared plus 7 sine x equals 7. So now we're all in terms of sine, which is helpful. But before we can move on, we need to distribute and get rid of these brackets. So I'll multiply the 4 in. 4 minus 4 sine squared plus 7 sine equals 7. Now that we're all kind of cleaned up here, the next thing we want to do, because we're working with a quadratic, is we want to move everything to one side so that way the other side equals 0. I'm going to choose to move everything to the right side so that way my leading coefficient, which is the one that's on the squared term, is going to be positive. So I'll move that 4 sine squared over first, becomes positive. I'll move the 7 sine x next. And we already had a 7 on this side, and I'm going to subtract this 4. So that's the equation that we're going to be working with. And again, if it's helpful for you, you can do the substitution and say let a equal sine x. So it looks more like a trinomial that we've worked with in the past. Again, we're left with a complex trinomial, so we want to find two numbers that multiply to 12 and add to -7. And those two numbers would be the -4 and -3. So again, because it's a complex trinomial, we can't just put these two numbers right away in the brackets. We'd have to decompose the -7. And then do some factor by grouping. So take a look at the first group and then the second group. So in the first group, 4a is common to both, leaving us with a minus 1. And in the second group, a -3 is common to both, leaving us with an a minus 1. Again, important note, these brackets must be identical before you can move on. Because they're identical, essentially what we're doing is factoring it out of the two terms. So first term, second term, let's take out the a minus 1, leaving us with 4a for our first term and minus 3 for our second term. So factored out. Now again, we're solving here, so I want to know what a equals. So in this case, a would be equal to 1, and in the second case, if I let this equal to 0, move the 3 over and divide by 4, we would be left with a equals 3 over 4. But again, a was never part of the question, so we need to replace the a with the sine x. So essentially, it's really sine x equals 1 and sine x equals 3 over 4. So at this point, our job is to find out what possible values of x will give us a ratio of 1, and then what possible values of x will give us a ratio of 3/4. So we'll work on this side. Now, like I said earlier, whenever your sine graph or cos graph equals 1, I find it's always easier just to take a look at the graph because the values just come so easily. So here's a quick sketch of our sine graph. So 0, 90 degrees, 180 degrees. Here's 270, and then finally 360 there. So between 0 and 360 degrees, sine hits its maximum only once at this point here. So what angle will give you the maximum? The angle is 90. Again, the alternate way to do this is you can take this equation here and find the inverse, and you should also get 90. Okay, now for our second case. Our second case here, we have sine x equals 3 over 4. So we'll go ahead and determine which quadrants sine is positive, because our ratio here, 3 over 4, is positive. Well, sine is positive in the first quadrant and in the second quadrant. So we do know that sine is y over r, but just for a second, I'll plot it on the graph here, 3 and 4. Do we have any special triangles with side lengths 3 and 4? Unfortunately, no. So we're going to have to go a different way in finding that related acute angle. So what we're going to do is use the inverse. So our related acute angle, I'll call it x related, is really just do the sine inverse of 3 over 4. So if you worked that out, the related acute angle on your calculator is approximately round to the nearest whole degree, so it's about 49 degrees. So that tells me that this related acute angle here is 49 degrees, and this one here is 49 degrees. Now that we know that, we basically go ahead and use the same method we did before to find our two possible values for x. So we'll start in standard position and rotate counterclockwise until we hit the first terminal arm. So Another possible value for x would be 49 degrees, straight off this diagram here. And then our final graph, actually I'm going to call that x2 because we found x1 over here, so this will be our second value for x. And then finally, start in standard position and rotate counterclockwise. So we went almost 180 degrees, but we stopped 49 before that. So our third possible value for x would be 180 minus the 49 degrees, giving us 131 degrees. Okay, so if you wanted to write a nice, neat therefore statement, so our possible values for x, 49 degrees, 90 degrees, and 131 degrees. So again, just take note that whenever you don't have special triangles, you have to do the inverse to find that related acute angle. So it might be a good idea to put a little star or something beside that so it'll help you remember. And that's it for today's lesson. If you have any questions, please make sure you ask in class. Take care, guys.